Could you travel through a wormhole and survive? Imagine someone opens a door in front of you, not to another room, not to another country, not even to another planet. A door to another star. No rocket, no fuel, no waiting 20,000 years while your snacks expire and your bones file a complaint. Just a tunnel through space time. One side is here, the other side is somewhere impossible. A galaxy away, a century away, maybe the edge of the universe. Someone points at it and says, "Step through." Now, most science fiction asks one question: could a wormhole exist? But that is not the question I care about. The better question is, could you survive it? Because science fiction treats wormholes like cosmic hallways. You enter here, you exit there. Maybe there's dramatic blue lighting. Maybe someone says, "Hold on." And then everyone holds on to a tiny railing because apparently the entire safety plan is the upper body strength. But real physics is less polite. A hallway has halls, a wormhole has gravity, a hallway has an exit, a wormhole might collapse. A hallway does not try to stretch your body into long biological noodle. A wormhole might. So today, let's ask it properly. If the universe gave us a shortcut, would the shortcut let us arrive, or would it kill us before the first sightseeing photo? What a wormhole is supposed to be. A wormhole is usually described as a tunnel through space-time. Not just space, space-time. That matters because in Einstein's general relativity, gravity is not just a force pulling things down. Gravity is connected to the shape of space-time itself. Mass and energy curve spacetime. Objects move through that curved spacetime. This is why planets orbit stars. This is why light bends near massive objects. This is why black holes exist. The sci-fi idea of wormhole is simple. If space-time can curve, maybe it can curve so much that two distant places connect. Instead of traveling across the surface of the universe, you can go through a shortcut. The usual analogy is a piece of paper. Put two dots on opposite sides. Normally, to get from one dot to another, you travel across the paper. But if you fold the paper so the two dots touch, the distance becomes tiny. A wormhole is the universe doing that, except with space-time and with a few arts and crafts supplies. It sounds elegant, it sounds possible. And mathematically, wormhole-like structures do appear in some solutions to Einstein's equation. This is why the idea is not pure fantasy. It's not like saying, what if the moon was made of cake? Though honestly, NASA would have investigated by now. Wormholes come from real mathematical possibilities. But mathematical possibility is not the same as travel brochure. The equation may allow a shape. That does not mean a human body can pass through it. The famous early idea is called an Einstein-Rosen bridge. Einstein and Nathan Rosen described a kind of bridge in spacetime in 1935. Later, this idea became associated with wormholes in popular imagination, and science fiction took that and said, perfect, cosmic tunnel, galaxy shortcut, add some glowing rings and emotional intense music. But the original Einstein-Rosen bridge was not meant to be a usable travel portal. And the classic version has a serious problem. It comes too quickly, closes too quickly. So quickly that even light cannot cross from one side to the other before the bridge pinches off. That is a problem. Not a small problem. That is not we forgot to pack enough oxygen. That is, the tunnel disappears before the fastest thing in the universe can get through. If light cannot make it, you're not making it. You're mostly water and anxiety. So, the classic Einstein-Rosen bridge is not a safe tunnel. It is more like the universe briefly making a doorway and slamming it shut before anyone can say, wait, I left my charger. Traversable wormholes are the upgraded version. Okay, so later physicists studied what it would take to make a wormhole that could actually be crossed. That is a traversable wormhole. That means a wormhole with a throat that stays open long enough for something to pass through. Not just light, a person, a spaceship, a camera. A very confused sandwich. In 1988, physicists Michael Morris and Kip Thorne described a famous model of traversable wormholes. This is the version closer to what science fiction wants. A tunnel with two mouths, a throat connecting them, a shortcut across space-time. But there was a catch, a very expensive catch. To keep the wormhole open, the throat needs something strange. Exotic matter. Not exotic like mango flavored tea, exotic like negative energy density. Matter or energy that behaves in a way ordinary matter does not. Normal matter has positive energy density. It gravitates in the usual way. It tends to help spacetime curve inwards. But a traversable wormhole would need something that counteracts collapse, something that holds the throat open, something that says to gravity, no, actually, you're not closing today. This is where sci fi dreams hits the engineering wall. We do not know how to gather or create the kind of exotic matter needed for a large, stable, human traversable wormhole. Tiny quantum effects can involve negative energy in limited ways, but that is not the same as building a star sized cosmic tunnel with a welcome mat. The universe may allow the concept on paper, but the materials list is currently absurd. The wormhole has to be big enough. Let's say we somehow solve the exotic problem. Big assumption. I mean, massive assumption. An assumption wearing a crown and demanding tribute. Now, we need the wormhole to be large enough. If the throat is too small, you're not traveling through it. You're becoming part of a very unpleasant physics demonstration. A human sized wormhole would need to have a throat big enough for a person or a spacecraft to pass through safely. But size is not just about fitting, it's about forces. The smaller and more sharply curved the wormhole is, the more intense the space-time curvature may be. And intense curvature can mean intense tidal forces. Tidal forces happen when gravity pulls more strongly on one part of an object than another. Your feet and your head are at a slightly different positions. If gravity changes sharply across that distance, your feet could be pulled much harder than your head. That stretches you. Near extreme objects like black holes, tidal forces can become strong enough to tear objects apart. This is something called spaghettification, which is a funny word for an extremely unfriendly experience. Physics really looked at being stretched to death and named it after a pasta. Very calm feel, very normal. So, if a wormhole has violent tidal forces near the entrance or inside the throat, survival is over. A human transversible wormhole would need gentle tidal forces. The difference in gravity across your body would need to be small enough that you remain a person, not a noodle, not a mist, not a regret. And the tunnel has to be stable. Even if the wormhole is big enough, it has to stay open. That is the central problem. A wormhole is not useful if it collapses while you're inside. That is worse than an elevator getting stuck. At least an elevator does not convert your travel plan into space-time obituary. For a safe journey, the throat must remain stable before, during, and after entry. It cannot pinch off, it cannot fluctuate violently, and it cannot develop a horizon that traps you. It cannot collapse because your spaceship entering changed the energy balance. That last part matters. You are not weightless in the equation. A traveler carries mass and energy. A spacecraft carries more. passing through the wormhole could affect geometry. So, the wormhole does not just need to exist, it needs to tolerate being used. A bridge that collapses when someone steps on it is not a bridge, it's a dramatic suggestion. The entrance must be deadly. In sci fi, the wormhole entrance is usually beautiful: a glowing spear, a spinning lens, a shimmering doorway. The kind of thing that makes astronauts stare meaningfully while the soundtrack does cardio. But if a real wormhole existed in space, the area around it might not look friendly. It could gravitationally lens light. It could distort the view behind it. It might collect matter or radiation near its mouth. Depending on where it is and how it formed, there could be dangerous particles, intense radiation, or debris. If the wormhole mouth is near a black hole or other extreme object, the environment could be lethal before you even reach the tunnel. That is very rude entrance policy. Imagine traveling across space for years and the door itself says, access denied by radiation. So, survival is not just about the throat, it's about the neighborhood. Where is the wormhole? What is around it? Is matter falling in? Is radiation trapped or amplified? Are there intense magnetic fields? Is the mouth stable? Can we approach it without being cooked, stretched, or shredded? The cosmic shortcuts still need parking. The destination is also a problem. Let's pretend the entrance is safe. The throat is stable. The tidal forces are gentle. The exotic matter is handled. The ship enters. Everyone survives the tunnel. Great. Where do you come out? Science fiction often treats the exit like a known address. Wormhole to Saturn, wormhole to another galaxy, wormhole to the dramatic third act. But real spacetime does not owe us GPS. If a wormhole connected two distant regions, we would need to know exactly where the other mouth is. Is it a star? Is inside a nebula? Close to a black hole? Is it in intergalactic space, moving relative to us, surrounded by radiation, inside a region where gravity is deadly? A survivable wormhole needs a survivable destination. A shortcut to the inside of a star is technically efficient, briefly. Very briefly. Also, the two mouths might not stay still relative to each other. They could move, they could experience different gravitational fields, they could experience different time rates, which brings us to a weird consequence.